Welcome to the lecture on Introduction to Beams. In this lecture, you will understand what a beam is and its types. You will then know about the different supports supporting a beam and the corresponding unknown parameters. We will then talk about the types of loads acting on the beam. We then try to understand two principles, namely the method of sections and the principle of superposition or superimposition for a linear system. Lastly, we will talk about the resisting forces and resisting moment developed within a beam's cross-section in response to the loads together with the sign conventions, namely axial force, shear force, and bending moment. So, what is a beam? A beam is a structural member which primarily supports a number of lateral or transverse or perpendicular loads across the beam's longitudinal axis. The beam may withstand axial forces or inclined forces also, though comparatively small in most cases. The applied forces, that is loads, and applied moments produce reaction forces and reaction moments in certain cases at the beam's support points. They also cause transverse or lateral deformations called deflections over the length of the beam due to bending, leading to the generation of bending and shear stresses and strains. Beams may be made up of a single material throughout the length, or a combination of one material reinforced with another stronger material may also be used. For example, a wooden beam reinforced by steel plates. This compound beam is called a flitched beam or composite beam and is mainly used to make the structure lighter and cheaper as compared to solid steel beams for the same strength. Flitched beams are also stronger than timber or wood and require less depth for building than a wooden beam would if it had the same amount of strength. The biggest disadvantage of using flitched beams is the high labor cost involved in their manufacture, hence being mostly used for historic renovations, that is, reinforcing existing lumber supports and for aesthetic purposes. The flitched beams also take a longer time to put together than those made only from timber. This means the amount of time needed to complete a work project will increase. We shall analyze flitched beams later in the chapter of pure bending or flexure. Let us now understand a few important types of beams. This is known as a simply supported beam. This is a cantilever beam. This is an overhanging beam where some portion overhangs or extends further from the supports at one or both the supports. And this is a fixed beam. For convenience, we draw a schematic diagram showing the actual beam with depth as simply a line with no depth representing the neutral axis or neutral surface of the beam. Just to inform, a neutral axis or neutral surface is one which passes through the centroid of the beam's cross-section and which may deform but shows no signs of elongation or contraction before and after the loads are applied. Neutral axis also coincides with the centroidal axis if the beam is initially assumed to be perfectly straight or prismatic. We shall learn more on this in the chapter of pure bending or flexure. There are still other variations of beams, namely beams with axial force release, beams with shear force release, and beams with bending moment release, or simply internal hinges, which shall be discussed later in this course. Let us now understand the types of support. This is known as the roller support and is schematically represented as a triangular slab with rollers beneath it, or simply as a roller and the fixed surface beneath them. This is the hinge or pin support, and this is the fixed support. In fixed support, an extended portion of the beam is inbuilt within the wall, or the beam is simply welded to a column or rigidly fixed by using frames and fasteners. Roller support provides only one unknown reaction force perpendicular to the surface on which it is placed. A pin or hinge support provides two reaction forces, one along the longitudinal axis or parallel to the fixed surface, and one perpendicular to it. Both the roller support and the pin or hinge support do not provide any resistance to the bending moment. A fixed support provides a reaction force each in the horizontal and vertical direction, as in the case of a hinge support, but additionally provides an unknown reactive moment. Hence, the number of unknowns in a roller support is 1, for a hinge or pin support it is 2, and for a fixed support it is 3. For a bent beam, you observe that there are slopes obtained at the location of roller and hinge supports, while the slope is 0 at the location of fixed support. The slope at the support is simply the angle made by the tangent line to the bent beam with respect to the unbent beam. These unknown reaction forces and moments, if any, need to be first calculated for a given beam with loadings and supports based on the three equilibrium laws of the entire beam. The pin or hinge support and the roller support together are called simple supports. Hence the name simply supported beam, as both of these types shall be used to support the simply supported beam. A word of caution. Note that we do not represent a simply supported beam supported by two hinge supports and no roller support, as this would make the number of unknowns in the structure as 4, that is, 2 unknowns for each hinge support, while the number of equations available to solve for the 4 unknown reactions are only 3, that is, based on the 3 equilibrium equations. Namely, summation of forces in the x direction is 0, the summation of forces in the y direction is 0, and the summation of moments about any point along the beam's length is equal to 0. Since the number of equations available, that is 3, for static equilibrium is less than the total number of unknowns, that is 4, in the beam with two hinge supports, this makes the structure statically indeterminate. That means we cannot find a definite solution or value for each of the 4 support reactions unless an additional equation to the 3 equations is added. Likewise, we do not even represent a simply supported beam with 2 roller supports in general without any hinge support. 2 roller supports would be okay if only transverse loads are acting on the beam, but in general we may expect some horizontal loads or inclined loads also to be present on the beam, for which the 2 roller supports would not be able to withstand the horizontal forces, and this would become an unstable structure. That means there is no horizontal equilibrium maintained, and the structure would simply keep moving along the direction of the horizontal force. Hence, a typical simply supported beam in general is represented as one that is supported by one roller support and one pin or hinge support. Let's now focus on the various loads that may act on the beam. The simplest one is the point load, represented by an arrow, and acts in a very narrow portion along the beam's length. If a number of point loads of equal magnitude is spread across a considerable distance along the beam's length, we call it a uniformly distributed load. We specify it by the load acting per unit length. Schematically, it can be shown as an array of arrows arranged sideways, pointing either in up or down direction, or as an array of semicircles touching each other side by side. The resulting load value is a rectangular area generated and is shown to act at its centroid. If the distribution of load is linearly changing over a distance, it is called uniformly varying load, and its resultant acts at the centroid of the triangular area generated. Lastly, we have the applied or concentrated moments acting at a point along the beam's length about the axis perpendicular to the screen. Let's now understand the two important principles used in strength of materials for finding the unknown resisting forces and moments at any point within a beam, namely the method of sections and the principle of superposition or superimposition. The method of sections states that if an entire body under a set of applied loads and moments is in equilibrium, then any small part of it created by virtue of an imaginary section should also be in equilibrium. To make it simple, let's say that an imaginary section or cutting plane divides a beam into two parts, A and B. Then, if the entire beam was in equilibrium before cutting, then A or B when taken separate are both in equilibrium. This is because we show the internal resisting forces and moments developed at the section for any part under consideration, which replace the adjacent part removed after taking the section. These resisting forces and moments set up at every point within the section along the beam length are known as axial force, that is, acting along the longitudinal axis, shear force, that is, acting perpendicular to the axis and tangent to the cross-sectional area, and resistive bending moment, which is simply called as bending moment for convenience here. The principle of superposition or superimposition as applicable for a linear system states that the result of a number of loads acting on the beam can be taken as the summation of the results arising from each load acting separately. We assume that the system is linear, meaning that the behavior between input forces and output deformations in our case can be described by a straight line graphically or by a linear equation mathematically. Let's denote the axial force as AF with the suffix x. We pronounce it as axial force at x, the shear force as shear force at x, and the resisting bending moment as bending moment at x, or simply m at x. The axial force at x can be described in detail as the axial force generated in the cross-section after taking an imaginary cut which is at a distance of x from the reference. The reference can be taken as the end of the beam for the part which is assumed to be in equilibrium. So, considering part A in equilibrium, the left end of the beam shall be the reference point, and considering part B in equilibrium, the right end of the beam shall be the reference point. Whichever part of the beam is considered to be in equilibrium for our analysis, remember that the same value of resistive force or moment at the section results. Lastly, let's talk about the sign conventions for the axial force, shear force, and bending moment. Sign convention is important for the purpose of interpretation on the part of the analyst. There is no fixed rule. For example, a person may wish to consider the axial force as positive if in the presence of the applied horizontal load creates tension on the part created by the section, while another person may wish to consider it as negative for tension. As long as the correct values are found out, it depends on the person performing the calculations to interpret it in the correct way. Whether to assign it as positive or negative is a matter of convenience, but interpretation needs to be correct. So, we try to follow the following sign conventions that are described by major text and reference books on the subject. Axial force acting on a section at distance x from the reference, or AF at x in short, is taken as positive if the combined effect of the axial force and the horizontal load is to elongate the part under study and vice versa. Shear force at x is taken as positive if the combined effect of the shear force and the applied transverse load is to create a clockwise couple and vice versa. Bending moment at x is taken as positive if the part under consideration bends about the section in response to the applied load or applied moment so that it can hold some liquid when it is poured from the top over the bent beam. This is termed the sagging effect, which is considered positive. If the part of the beam bends about the section in such a way that the poured liquid from the top of the beam drops down, then it's a negative bending moment at x. This is called the hogging effect, which is considered negative. We are now ready for the analysis of the resistive forces and resistive moments developed at any cross section along the length of the beam under a system of loads and applied moments. We shall consider a simple example of a simply supported beam with an inclined load acting at the center of the span in the next lecture.